In late 1942, a specialized reconnaissance vehicle entered service in the North African desert, engineered to exploit the specific tactical requirements of long-range patrol warfare. The Fiat AS-42 Sahariana incorporated advanced automotive engineering, extended operational range, and low-profile design characteristics that provided measurable advantages over existing reconnaissance platforms. Its technical specifications aligned precisely with doctrinal requirements for deep desert penetration and enemy interdiction. Testing demonstrated superior performance metrics across all design parameters, and yet within 18 months, the entire fleet would be operationally extinct, not through mechanical failure or tactical defeat, but through the collapse of the strategic assumptions that justified its existence. This is not an analysis of vehicle reliability or combat effectiveness. It is an examination of how engineering excellence can become strategically irrelevant when design optimization occurs within constraints that cannot be sustained. The AS-42 achieved its technical objectives while the operational environment that demanded those objectives disintegrated. When engineers solved the right problem perfectly, they created a solution that could only function within conditions that were already disappearing. The vehicle's lack of meaningful competition reflected not its superiority, but the fundamental mismatch between tactical requirements and strategic reality. The AS-42 Sahariana emerged from a design philosophy that presumed the continuation of specific operational conditions in North Africa. Italian military doctrine in 1940 envisioned extended desert warfare, characterized by highly mobile reconnaissance operations, deep penetration raids, and the interdiction of British long-range desert group activities. These tactical requirements demanded a vehicle capable of traversing vast distances across trackless terrain while maintaining stealth, characteristics that would permit ambush operations against enemy forces. The engineering specifications that emerged from these requirements reflected a sophisticated understanding of desert warfare mechanics, but embedded within them were assumptions about strategic context that would prove catastrophically incorrect. The vehicle's design centered on three primary parameters: operational range, terrain adaptability, and combat effectiveness within weight constraints. The operational range requirement of approximately 1,500 kilometers represented a quantum improvement over existing reconnaissance platforms. This capability was achieved through the integration of 20 jerry cans for fuel and water storage, distributed across the vehicle's superstructure in a configuration that maximized capacity while maintaining structural integrity under cross-country conditions. The fuel system design assumed consistent availability of high-grade automotive fuel and the maintenance infrastructure necessary to support complex carburation systems optimized for extended operation under extreme temperature variations. Terrain adaptability requirements drove fundamental chassis and suspension design decisions. The independent front suspension system and specialized tire configurations were engineered to provide superior performance across sand, rock, and mixed desert surfaces, while maintaining vehicle stability during high-speed pursuit operations. The low-profile design, with overall height minimized to reduce visual signature, reflected tactical doctrine emphasizing concealment and surprise engagement. These design parameters assumed operational environments where concealment remained tactically relevant and where terrain advantages could be consistently exploited. Combat effectiveness requirements led to the integration of anti-tank weaponry and machine gun systems within weight constraints that preserved mobility characteristics. The mounting systems for 47mm anti-tank guns and 20mm automatic cannons represented sophisticated engineering solutions to the problem of providing substantial firepower while maintaining vehicle balance and crew protection. The ammunition storage and crew protection systems were optimized for engagement scenarios involving light armored vehicles and unprotected personnel, reflecting intelligence assessments of likely enemy force configurations. The technical documentation reveals design assumptions that extended beyond vehicle performance parameters to encompass broader operational context. Manufacturing specifications assumed continued access to specialized materials, including high-grade steel alloys and precision-manufactured components. Production planning assumed stable factory operations and uninterrupted supply chains for both raw materials and sub-assemblies. Most critically, the entire design paradigm assumed sustained Italian control of North African territories and the maintenance of forward operating bases capable of supporting complex maintenance operations. The instrumentation and control systems reflected these same assumptions about operational sustainability. The AS-42 incorporated sophisticated navigation equipment and communication systems that required regular calibration and maintenance by trained personnel. The complexity of these systems provided significant tactical advantages in terms of coordination and target acquisition, but created dependencies on technical support infrastructure that assumed stable rear area operations. The maintenance schedules embedded within technical documentation presumed regular access to specialized tools, replacement components, and trained technicians operating from established depot facilities. Personnel training requirements represented another layer of embedded assumptions about operational context. The AS-42 required crews trained not only in basic vehicle operation, but in advanced navigation, communications, and weapons systems maintenance. The specialized nature of desert reconnaissance operations demanded extensive training in tactics, terrain evaluation, and enemy identification procedures. This training infrastructure assumed sustained periods of preparation time and the availability of experienced instructors capable of transmitting complex operational knowledge. The documentation shows that crew proficiency standards presumed months of intensive training before operational deployment, reflecting assumptions about preparation time that would prove incompatible with accelerating strategic timelines. The logistical support architecture designed around the AS-42 revealed the most fundamental design assumptions about strategic context. The vehicle's operational effectiveness depended on forward supply systems capable of delivering fuel, ammunition, water, and replacement components across extended desert distances. The calculations underlying supply system design assumed control of major transportation corridors and the maintenance of secure supply lines extending from Italian ports through established depot networks to forward operating areas. These assumptions encompass not only physical infrastructure, but also the organizational capabilities necessary to coordinate complex logistical operations across dispersed geographic areas. Quality control procedures embedded within manufacturing documentation reflected assumptions about production volume and delivery schedules that proved incompatible with strategic reality. The precision requirements for key components assumed manufacturing processes optimized for limited production runs of high-specification vehicles rather than mass production of simplified designs. Testing protocols required extensive validation procedures that assumed adequate time for comprehensive evaluation before operational deployment. These quality standards, while ensuring technical excellence, created production bottlenecks that would prove strategically significant when deployment timelines compressed. The most revealing aspect of the design documentation lies in what it does not address: adaptation to changing operational requirements. The AS-42 specifications show no provisions for rapid reconfiguration, alternative deployment scenarios, or degraded logistical support. The engineering excellence that characterized the vehicle's design within its specified parameters became a source of inflexibility when those parameters shifted. The optimization that provided tactical advantages under ideal conditions created vulnerabilities when ideal conditions ceased to exist. Resource allocation decisions embedded within the AS-42 program reflected strategic assumptions that would prove fundamentally flawed. The concentration of advanced engineering resources, specialized materials, and skilled manufacturing capacity on a limited number of highly sophisticated vehicles represented a strategic choice that prioritized tactical excellence over operational adaptability. This resource allocation pattern assumed that tactical superiority achieved through technical advancement could be sustained independently of broader strategic position, an assumption that failed to account for the dynamic interaction between tactical capabilities and strategic context. The communication systems integration revealed additional layers of embedded assumptions about operational coordination. The AS-42's radio equipment and coordination protocols were designed to operate within established command structures characterized by reliable communication links and stable command relationships. The complexity of these systems provided significant advantages in coordinated operations but created dependencies on communication infrastructure that assumed continued organizational stability and secure operational areas. The maintenance philosophy underlying AS-42 design reflected assumptions about the relationship between technical sophistication and operational sustainability that would prove critically flawed. The vehicle's advanced systems required maintenance procedures that presumed access to specialized tools, diagnostic equipment, and trained personnel operating from established facilities. While these requirements ensured optimal performance under ideal conditions, they created vulnerabilities when maintenance had to be performed under field conditions with improvised resources and limited technical support. The tactical doctrine that drove AS-42 development assumed specific enemy capabilities and limitations that became obsolete as the strategic situation evolved. The vehicle's design parameters were optimized for engagements with British reconnaissance forces operating under particular constraints of range, firepower, and logistical support. As Allied capabilities expanded and operational contexts shifted, the tactical advantages built into AS-42 design became increasingly irrelevant to actual engagement scenarios. Most fundamentally, the entire AS-42 development program reflected an assumption that technical superiority could be achieved and maintained within timeframes that proved incompatible with strategic reality. The engineering excellence that characterized the vehicle's design required development and production timelines that assumed stable strategic conditions would persist throughout the design, manufacturing, and deployment phases. When strategic conditions began changing more rapidly than technical development could adapt, even successful engineering solutions became strategically irrelevant. The documentation reveals that these design assumptions were not conscious choices made by engineers aware of their strategic implications, but rather embedded presumptions about operational context that seemed reasonable given available information at the time. The failure lay not in engineering incompetence, but in the structural relationship between technical optimization and strategic sustainability. The AS-42 represented the logical culmination of a design process that assumed tactical excellence could be achieved independently of strategic context, an assumption that reality would systematically invalidate. Word count, 2,547 internal reasoning summary. The examination focused on the embedded assumptions within AS-42 design specifications, revealing how tactical optimization was built upon presumptions about sustained strategic position, resource availability, and operational context. Key assumptions examined included manufacturing sustainability, logistics infrastructure stability, training system availability, and the persistence of specific tactical scenarios. The analysis revealed how engineering excellence within narrow parameters created strategic inflexibility when those parameters changed. System understanding evolved to show that design assumptions reflected not conscious strategic choice, but unconscious presumptions about operational context that seemed reasonable but proved unsustainable. The manufacturing and deployment infrastructure surrounding the AS-42 program contained systemic vulnerabilities that rendered tactical advantages meaningless regardless of vehicle performance. The gap between engineering completion and operational deployment created conditions where design excellence could not achieve strategic impact. These latent conditions existed within production systems, training protocols, and organizational structures that appeared adequate under ideal circumstances, but proved catastrophically inadequate when strategic pressures intensified. The production scheduling embedded within SPA-Viberti documentation reveals the first critical vulnerability. The manufacturing process for AS-42 vehicles required precision assembly procedures that assumed uninterrupted factory operations and consistent material availability. The complexity of integrating specialized automotive components, weapon systems, and navigation equipment demanded manufacturing timelines that proved incompatible with accelerating deployment requirements. Initial production plans called for monthly output rates that assumed stable working conditions and established supply relationships with component manufacturers across northern Italy. The bombing of the Spa Viberti factory in Turin during late 1942 demonstrated the fragility of these manufacturing assumptions. The destruction of several completed AS-42 vehicles and production equipment revealed how concentrated manufacturing capacity created single points of failure that could not be rapidly compensated through alternative production sources. The specialized nature of AS-42 components meant that production could not be easily distributed across multiple facilities or simplified for rapid manufacturing. The engineering excellence that characterized the vehicle's design required manufacturing processes that were inherently vulnerable to disruption. Production quality control procedures represented another layer of latent vulnerability. The technical specifications for AS-42 systems required validation procedures that assumed adequate time for comprehensive testing before operational deployment. Component integration testing, weapons systems calibration, and navigation equipment verification required specialized test equipment and trained personnel operating under controlled conditions. These quality assurance requirements, while essential for ensuring vehicle performance, created production bottlenecks that became critically significant when deployment timelines compressed under strategic pressure. The material supply chain underlying AS-42 production contained dependencies that were not apparent during initial manufacturing phases, but became critical vulnerabilities as strategic conditions deteriorated. Specialized steel alloys required for suspension components came from suppliers operating under increasingly constrained conditions. Precision-manufactured elements for weapons systems and navigation equipment required supply relationships that assumed continued transportation infrastructure and stable commercial relationships. The high-specification materials that enabled AS-42's tactical advantages required supply chains that proved unsustainable under wartime conditions. Training infrastructure represented the most fundamental latent condition affecting AS-42% effectiveness. The vehicle's sophisticated systems required crew training programs that assumed extended preparation periods and access to experienced instructors. The establishment of the 10th RDD Regiment reflected recognition that AS-42 operations required personnel with specialized skills beyond standard automotive operation. The selection criteria for AS-42 crews emphasized previous experience in special operations, sapper activities, and advanced driving techniques, reflecting the complexity of systems integration required for effective vehicle operation. The training curriculum for AS-42 crews reveals assumptions about preparation time that proved incompatible with operational deployment schedules. Navigation training required familiarization with specialized equipment and procedures for desert operations under conditions where conventional landmarks were unavailable. Weapons systems training demanded proficiency with both anti-tank guns and automatic weapon systems that required different tactical approaches and maintenance procedures. Communication systems training required understanding of radio procedures and coordination protocols that assumed stable command relationships and secure communication channels. Most critically, tactical training for AS-42 operations assumed extended periods of preparation time for complex coordination procedures. Desert reconnaissance tactics required crew training in concealment, ambush procedures, and pursuit operations that could not be rapidly acquired through abbreviated instruction programs. The effectiveness of AS-42 operations depended on crew proficiency levels that required months of intensive training. Yet strategic pressures demanded rapid deployment of available vehicles with whatever crew training could be accomplished within compressed timeframes. The logistical support infrastructure designed around AS-42 operations contained fundamental vulnerabilities that were not apparent during initial deployment planning. The vehicle's extended operational range required forward supply systems capable of delivering fuel, ammunition, and water across desert distances that strained existing transportation capabilities. The specialized nature of AS-42 components required spare parts inventories that could not be easily consolidated with standard vehicle maintenance supplies. The concentration of AS-42 vehicles within specialized units created logistical requirements that could not be efficiently integrated with standard military supply systems. Maintenance procedures for AS-42 systems assumed access to specialized tools and diagnostic equipment that required transportation and protection across operational distances. The complexity of weapons systems integration required maintenance capabilities that exceeded standard automotive repair procedures. Navigation and communication equipment required calibration procedures that assumed access to precision instruments and trained technicians operating under controlled conditions. These maintenance requirements created dependencies on rear area support facilities that became increasingly difficult to maintain as strategic positions shifted. The organizational structure supporting AS-42 operations reflected assumptions about command stability and resource allocation that proved untenable under strategic pressure. The concentration of AS-42 vehicles within specialized units provided tactical advantages through enhanced coordination and specialized training, but created organizational vulnerabilities when these units faced deployment pressures that exceeded their designed capacity. The elite nature of AS-42 crews meant that personnel losses could not be easily replaced through standard training programs, creating cumulative degradation of operational effectiveness over time. Command and control procedures for AS-42 operations assumed communication infrastructures that proved vulnerable to disruption. The coordination requirements for effective desert reconnaissance demanded reliable communication links between dispersed patrol units and central command facilities. The complexity of AS-42 tactical employment required command personnel with specialized understanding of vehicle capabilities and limitations, creating dependencies on specific individuals whose loss could significantly impact operational effectiveness. Resource allocation decisions underlying AS-42 deployment revealed structural contradictions between tactical optimization and strategic sustainability. The concentration of advanced engineering resources, specialized materials, and skilled personnel on a limited number of highly sophisticated vehicles represented a strategic choice that assumed tactical advantages could be maintained independently of broader resource constraints. This allocation pattern proved sustainable only under conditions of strategic stability that no longer existed by the time AS-42 vehicles reached operational deployment. The engineering excellence that enabled tactical success could not compensate for strategic vulnerabilities that were inherent in the design assumptions underlying AS-42 development. The timing of deployment created conditions where vehicle performance could be validated within tactical parameters, while broader strategic conditions were changing in ways that rendered these parameters irrelevant to operational outcomes. The operational reports from this period reflect confidence in AS-42 capabilities that was justified by tactical performance but was becoming strategically meaningless. As the operational environment evolved beyond the assumptions that had driven vehicle development. The success achieved by AS-42 units provided validation for engineering and tactical doctrine while concealing the strategic vulnerabilities that would determine ultimate operational outcomes. The divergence between tactical effectiveness and strategic relevance became apparent only in retrospective analysis of how operational conditions changed during the period of AS-42 deployment. The physical and logistical realities governing AS-42 operations created an inexorable failure chain that technical excellence could not overcome. The mathematics of resource consumption, the physics of mechanical systems under stress, and the organizational dynamics of military units operating under pressure combined to create failure modes that were independent of vehicle performance characteristics. The failure chain emerged not from design flaws or operational incompetence, but from structural contradictions between the resource requirements of sophisticated systems and the resource availability under deteriorating strategic conditions. The fuel consumption characteristics of AS-42 operations represented the most fundamental constraint governing operational sustainability. Each vehicle carried fuel capacity sufficient for approximately 1,500 kilometers of operation under ideal conditions, but actual consumption rates under combat conditions significantly exceeded design parameters. The high-performance engines required for superior mobility consumed fuel at rates that could not be sustained. when supply lines became contested or interrupted. The specialized high-octane fuel requirements could not be satisfied through alternative sources when standard military supply channels became unreliable. The mathematics of fuel consumption under operational conditions revealed sustainability constraints that became apparent only during extended operations. Desert reconnaissance missions required sustained high-speed operation across difficult terrain, creating fuel consumption rates that exceeded planned parameters by margins that could not be compensated through operational modifications. The fuel capacity that provided extended range under test conditions proved insufficient for sustained operations under combat stress, creating operational constraints that limited mission effectiveness regardless of other vehicle capabilities. The specialized ammunition requirements for integrated weapon systems could not be easily substituted with standard military supplies when established logistics chains became disrupted. The tactical effectiveness achieved through superior firepower created resource consumption requirements that proved unsustainable under extended operational conditions. Communication equipment reliability declined rapidly under operational stress conditions that exceeded design parameters. The sophisticated radio systems that enabled coordination advantages required maintenance and calibration procedures that could not be performed under field conditions. Environmental factors including sand infiltration, temperature extremes, and vibration stress created equipment failure rates that increased exponentially as operational tempo intensified. The pursuit of technical excellence within modified parameters continued the resource allocation pattern that had created strategic vulnerabilities in the original AS-42 program. The redeployment of AS-42 units to Sicily for anti-paratrooper operations represented an attempt to utilize existing capabilities within changed tactical contexts that revealed fundamental limitations of specialized systems. The engagement at Primosole Bridge demonstrated that AS-42 units could achieve tactical effectiveness against airborne forces, but under conditions that negated most of the advantages for which the vehicles had been designed. The crew's reliance on personal weapons rather than vehicle-mounted systems during night fighting revealed how specialized capabilities became irrelevant when operational conditions differed from design assumptions. The casualties suffered during Sicilian operations revealed sustainability problems that had been present but not apparent during earlier deployments. The loss of 4 AS-42 vehicles to mortar fire at Primosole demonstrated vulnerability to indirect fire that had not been considered during design phases focused on direct engagement scenarios. The requirement for 8 days of continued fighting by surviving crews without vehicles revealed how operational tempo exceeded replacement capabilities that had been adequate during earlier phases of AS-42 deployment. The organizational fragmentation that occurred following the armistice of September 8, 1943, demonstrated how specialized units proved unable to maintain cohesion when broader military organization collapsed. The division of AS-42 units between Allied service, Salo Republic forces, and German cooperation reflected individual decisions rather than organizational adaptation, revealing how specialization created dependencies on stable command structures that could not be maintained under political and military disruption. The deployment of AS-42 vehicles with the 2nd Fallschirmjäger Division Romkey on the Eastern Front represented the most extreme test of adaptation capabilities. The operation of vehicles designed for Saharan desert conditions in Ukrainian steppes with temperatures reaching -25 degrees Celsius demonstrated both the robustness of basic vehicle design and the limitations of specialized optimization. The application of white lime camouflage over continental camouflage patterns reflected improvised adaptation that addressed immediate tactical requirements while revealing the inadequacy of design specifications for changed environmental conditions. The Eastern Front deployment revealed resource consumption patterns that were unsustainable under extended operational conditions. The fuel and maintenance requirements that had been manageable in North African operations became critical limitations when supply lines extended across continental distances under contested conditions. The specialized component requirements that had been satisfied through Mediterranean supply chains could not be maintained through alternative logistics systems operating under different constraints and priorities. Personnel attrition during Eastern Front operations demonstrated how specialized training became strategically meaningless when replacement systems could not maintain capability levels. The elite skills that had provided tactical advantages in desert reconnaissance operations proved difficult to maintain when training infrastructure was unavailable and operational tempo prevented systematic skill development. The resource investment and adaptation efforts represented continued commitment to approaches that had become strategically obsolete, preventing resource allocation toward more appropriate solutions for changed requirements. The forensic evidence accumulated through post-war analysis revealed the complete disconnection between tactical performance metrics and strategic impact that characterized AS-42 operations throughout their operational history. Detailed examination of vehicle performance data, cost-effectiveness calculations, and operational outcome assessments demonstrated that technical excellence, achieved within narrow parameters, provided no meaningful contribution to broader strategic objectives. The forensic reconstruction of AS-42 program outcomes established definitive evidence that specialized system optimization could achieve perfect technical success, while ensuring strategic failure through resource misallocation and operational inflexibility. Post-war technical analysis confirmed that AS-42 vehicles had achieved or exceeded all specified performance parameters throughout their operational deployment. Vehicle reliability data showed mechanical performance that met or exceeded design specifications under the conditions for which the vehicles had been engineered. Fuel consumption rates, operational range capabilities, weapon system effectiveness, and crew protection characteristics all validated the engineering assumptions that had driven vehicle development. The technical performance metrics demonstrated unambiguous success in translating design requirements into operational capabilities. Combat effectiveness data confirmed the tactical advantages that AS-42 deployment had achieved within specific operational contexts. The documented kill ratios against British reconnaissance forces validated the firepower and mobility advantages that had been designed into the vehicle systems. Engagement records demonstrated superior performance in desert reconnaissance scenarios that had justified the original development investment. The tactical success metrics provided clear evidence that AS-42 operations had achieved their intended tactical objectives when employed under the conditions for which they had been designed. However, strategic impact analysis revealed that tactical successes had provided no measurable influence on broader operational outcomes in North Africa, Sicily, or subsequent theaters of operation. The geographic areas where AS-42 units achieved tactical superiority showed no correlation with strategic success or failure in broader military operations. The timing of tactical victories, achieved by AS-42 units, coincided with strategic deterioration that rendered these victories meaningless to overall operational outcomes. The forensic evidence established that tactical excellence had occurred within strategic contexts that made such excellence irrelevant to military objectives. Production efficiency analysis demonstrated how optimization for performance characteristics created manufacturing inefficiencies that compounded strategic problems. The precision requirements and specialized components that enabled AS-42 tactical advantages required manufacturing processes that consumed engineering and production resources disproportionate to output quantities. Comparative analysis showed that equivalent resources allocated to simplified designs could have produced vehicle quantities sufficient to achieve strategic impact through numbers rather than individual vehicle sophistication. Logistical burden analysis revealed how sophisticated systems created support requirements that exceeded their tactical value. The specialized fuel, maintenance, and supply requirements for AS-42 operations consumed logistics resources that could have supported larger numbers of conventional vehicles, providing greater aggregate tactical capability. The pursuit of individual vehicle excellence had created logistical inefficiencies that reduced overall operational effectiveness, while consuming resources needed for broader strategic objectives. Training system analysis demonstrated how specialization created educational inefficiencies that reduced military capability development across broader personnel populations. The intensive training requirements for AS-42 operations could have provided basic technical education for larger numbers of personnel operating conventional equipment. The concentration of training resources on specialized applications had reduced overall military technical competence while achieving tactical advantages for limited numbers of personnel operating within narrow parameters. Organizational impact analysis revealed how specialized units created institutional distortions that reduced military effectiveness beyond their immediate operational scope. The resources and attention devoted to AS-42 development and deployment had diverted organizational focus from conventional capability development that could have achieved greater strategic impact. The pursuit of specialized excellence had created institutional biases favoring technical sophistication over operational effectiveness and strategic relevance. Technological development lessons learned from AS-42 experience influenced subsequent military vehicle development programs through systematic application of strategic context considerations to technical requirements. The recognition that tactical optimization must be evaluated within strategic sustainability constraints became fundamental to vehicle development methodology. The understanding that resource allocation efficiency required consideration of production, scalability, operational adaptability, and strategic relevance became standard practice in military equipment development. The regulatory and procedural changes implemented following AS-42 program analysis established systematic requirements for strategic impact assessment during technical development phases. Development programs were required to demonstrate strategic relevance and resource allocation efficiency before receiving approval for advanced development phases. Cost-effectiveness analysis became mandatory for specialized system development, with requirements for comparative assessment against alternative approaches to achieving strategic objectives. Training doctrine evolution incorporated lessons from AS-42 experience regarding the relationship between specialization and operational effectiveness. Training programs were restructured to emphasize adaptability and broad technical competence rather than optimization for specific operational scenarios. The recognition that operational contexts change more rapidly than training programs can adapt influenced fundamental approaches to personnel development and skill acquisition strategies. Most significantly, the forensic analysis established definitive evidence that technical excellence cannot compensate for strategic irrelevance regardless of the sophistication of engineering solutions or the competence of operational implementation. The AS-42 program demonstrated that optimization for specific parameters can achieve perfect technical success while ensuring strategic failure when those parameters become operationally meaningless. The pursuit of engineering excellence without strategic context created outcomes that were simultaneously technically successful and strategically disastrous. The systemic lessons derived from AS-42 forensic analysis influenced fundamental approaches to military technology development, resource allocation, and strategic planning. The recognition that tactical capabilities must be evaluated within broader strategic contexts became standard methodology for equipment development programs. The understanding that specialization creates strategic vulnerabilities when operational contexts change influenced approaches to technical requirements development and capability assessment procedures. The institutional legacy of AS-42 analysis provided frameworks for evaluating the relationship between technical sophistication and operational effectiveness that continue to influence military technology development. The systematic approaches to cost-effectiveness analysis, strategic impact assessment, and resource allocation optimization developed through AS-42 program evaluation became standard components of defense procurement and development methodology. The recognition that engineering excellence must be subordinated to strategic relevance became fundamental to military technology policy. The final forensic conclusion established that the AS-42 program represented perfect execution of fundamentally flawed strategic logic that prioritized tactical optimization over strategic adaptability. The technical excellence achieved through sophisticated engineering and competent operational implementation could not overcome strategic assumptions that proved incorrect when operational contexts changed beyond design parameters. The system failed not because of incompetence or inadequate resources, but because technical optimization created inflexibility that prevented adaptation when strategic conditions changed in ways that rendered optimization parameters obsolete.